Hello Kidlets, this is your fourth video. We are going to be looking at the Doppler shift and some fundamentals of telescopes. Yes, I apologize, I do not have much of a voice today. So to start out looking at the Doppler effect or the Doppler shift, this is an apparent change in wavelength, not an absolute change in wavelength, due to the motion of an object related to the position of an observer. So if we take a look at this car, we look at a police car with a siren. As that police car is moving this direction towards this observer is going to hear an increase in pitch. So you hear this when you hear an increase, a siren coming towards you. You can tell if it's moving towards you, away from you, due to the increase in pitch as it moves towards you and the decrease in pitch as it moves away from you. So in terms of sound, we hear pitch because sound is a wave. But in terms of light, we see a shift towards longer and shorter wavelengths. So it's the same effect applied to both light and sound. So in terms of sound, we hear the pitch. In terms of light, we would see as something approaches us, we would see that shift towards blue wavelengths, shorter wavelengths of light. And as it moves away from us, we would see things shifted towards the red. So we can also determine things rotation this direction. So if something is rotating towards us, we would see that side shifted blue. We would see the side rotating away from us shifted red. And we can use this to determine distance as well. So the way this works for sound is, again, we see all of these waves. So the sound waves are going to be compressed as an object moves towards us and elongated as they move away. So if we look just at this top picture here, we could see this observer as the fire engine is moving towards them. It's compressing all the sound waves. And this observer where the fire truck is receding from it, it is elongating the waves. So this guy would hear a lower pitch, this guy would hear a higher pitch. So in terms of a star, this guy would see a blue shift of a star. This guy would see a red shift of a star, so as it's rotating away. In terms of galaxies, we can also determine that galaxies are all receding from themselves, from each other, and from us, because all galaxies in the universe appear to be redshifted. So that means the universe is expanding. We're seeing all galaxies moving away, and it's not actually the galaxies moving away, it's the space between them that's moving away. So space itself is expanding. So here's a little video that we will look at in class. A second video from Big Bang Theory we will also look at in class. And the Doppler shift can also be used to measure velocity. So we can see if we were to look at a spectra of a star, we could see that we have more spectral lines in the blue, which is indicative of something moving towards us. So if it's at rest, we see kind of neutral spectra. And if it's moving away from us, we see our red shifts here. So if you look just at the spectra that's in blue and red, so moving towards us, we could see shortened wavelengths here. Here we can see, look closely, you can see that shift is further to the right. And here you can see that shift is also further to the right. So looking right here at this spectral line, we can see as it's moving away from us, we have an increase in the reddened portion of the spectra. So now we're going to take a look at some different telescopes and some principles that govern those telescopes. So you can think about a telescope as being like a light collecting device. So all telescopes are doing is channeling light from space into one discrete receptor, which would be your eye. So just like a bucket that collects rainwater, a telescope is essentially a bucket that collects light. So this is how we gather information from space. So the larger the telescope, the more light it's going to gather, just like the larger the bucket, the more water it's going to gather. This is an image of the Hubble Space Telescope, and we can compare it about approximately the size of a bus. This is a very common amateur telescope. I have one just like this. You can see that he is looking through the side. A telescope like this would actually have an open top. You could reach all the way through it. So the mirror would appear right back here. Here we have, this is Mauna Kea in Hawaii. Yes, that is snow. So here we have modern professional telescopes that have a large opening dome, and the telescope itself is positioned inside. We'll see this when we go to the observatory. So some of the major features of telescopes have to do with the behavior of light. So we have reflection, where light is bounced off, and we have refraction, where we have a change in the velocity of the wavelength as it travels through a medium. So reflection deals with mirrors, and we have telescopes that use mirrors, and refraction deals with lenses. So there are also telescopes that use lenses. For example, Galileo's famous telescope, one of the first telescopes built. Remember, he hijacked the idea from Hans Lippershey, but his that he used to find and determine that we were not the center of the then universe was a refractor telescope. So this would be an example of a reflecting telescope. You can see that the eyepiece is located along the side. We have a mirror that is in the back. We have a flat mirror here. So in this case, this guy would be our primary mirror. This is our secondary mirror, and here would be our eyepiece. F has to do with the focal length, and the focal length is the total length of the travel path of the light. And the longer the travel path, the more focused an image can be, and the more distant an object can be. So a long focal length is good. And as we'll see, there are some telescopes that add in many, many more mirrors in order to extend that focal length. So here you have this part that is completely open. So usually these telescopes would have a cover, and that light is entering in and bouncing off a mirror, and that mirror is concave, so it's concentrating the light to a single focal point here and then bouncing it up to your eye. A refracting telescope is generally much, much longer because you don't have the use of mirrors to elongate that path of light. So in this case, we would have a lens. So take a look at how this lens is shaped. So opposite from concave, which we would have in mirrors, this would be convex. So in this case, we have multiple paths of light passing through, and you would have them concentrated at a place beyond the lens, whereas with a reflector, it is in front of the mirror. So in this case, this would be your total focal length, so from the lens to your eye. So most reflectors are very, very long. I'm sorry, refractors are very long. So that path of light is coming through, and then it is rerouted to reach a concentration point or a focal point there. So here again we can see an image of that path of light as it's traveling through both a lens and as it's traveling through a reflector, through a mirror, and where that focal length would be. And most all telescopes these days are reflectors. You can make them much smaller, you can make them much shorter. It's also much easier to produce a one-sided mirror. It's much lighter, easier to transport than an optically perfect on both sides lens. These lenses are also significantly heavier than a mirror because it has to be made of specific glass that has a very clear optical quality, and it has to be supported on both ends, which can be really hard depending on the type of tubing you have in your telescope. So refractors are much more difficult to make, and they used to make these very, very, very large, with multiple meter-size lenses that would have to be really strongly supported on both sides, and those were very difficult to make. It would take years to make glass of that quality. So most all telescopes nowadays are reflectors. If you're ever looking to buy a telescope and you're looking through it like a tube, that would be a refractor, and that's really not the way to go. Those are very difficult to use, very difficult to align, and your quality of your image is not so great. So here are some images of the secondary optics. So in terms of your refractor, so here we can see we have the lens up here concentrated to the single point here where it reaches your eye. So we have that convergence of light. So there's no secondary optics besides an eyepiece in a refractor. However, in a reflector, like I said before, we have that channeling of the light off of the mirror to our secondary mirror, so from the primary to the secondary, and then redirected back to the eye. So there are two other secondary optics. We have the secondary mirror and the eyepiece in a reflector. There's another type of telescope called a Schmidt-Cassegrain, which has many, many different mirrors in it to redirect light. So this is an example of a Newtonian reflector mirror. These are pretty darn expensive. I have a couple examples of these to show you in class, but this primary lens is the most important part. This is where the initial light from the star is hitting. So these have to be shaped in a very specific way. They have to be very, very clear. If you're ever interested in telescope making, you can actually buy these mirrors and sand them down, and it can take months, hundreds of hours literally, to sand them to the perfect quality to make it telescope material where you can actually see very distant objects. So one of the issues that refractors have, and one of the reasons that these are really not used very much anymore, is that it is very difficult for a lens to concentrate all of the different wavelengths of light to one singular point. Because the nature of a lens is to refract and slow the velocity, you're going to separate out each of the different components or colors of light. So you essentially get a prism effect, where you get your color of red, blue, and yellow would all be concentrated at different points. So this can make a really blurry image. and this is called chromatic aberration. So this would have been what Galileo used, and to minimize chromatic aberration, he would have made his telescope very, very, very long. So the longer the focal length, the less of this image. Another way to minimize this is by adding another secondary lens behind it, which can assist in concentrating that light to one singular point. So again, this is called chromatic aberration, and this is where you have each of the different colors, the components of visual light, that is concentrated in different portions. And that's just due to this lens that does not slow all the colors change their velocity at the same rate. One of the issues that can arise from reflectors is called spherical aberration, and this is essentially the blurring of an object simply due to the spherical nature of the mirror, due to the surface geometry of that mirror, and it can also happen with lenses as well. So it can appear distorted. So you can see this image is from Hubble, and even Hubble has spherical aberration, so you have to have corrective or adaptive optics to be able to give it this really clear image. And this is just something that all telescopes have. There's ways to minimize, but not ways to completely eliminate it. So that's why there's secondary optics and then advanced optics later on to modify the image. Seeing is a really important term and related to astronomical viewing, especially from ground level, and this is why we put telescopes up in space and on mountaintops, because seeing has to do with the clarity of the atmosphere. The more atmosphere above you, the more twinkling of stars you see. If you were actually out in space, you would not see stars twinkling at all, and that was one thing that the Apollo astronauts immediately noticed. This has to do with atmospheric instability. So for example, in Los Angeles, anytime we're going to use a telescope, we're going to see a lot of twinkling, a lot of blurring, and this also acts as a refractor for incoming starlight. So we would actually see them in a different place in the sky than where they are, because that starlight is passing through so much atmosphere. So darker skies generally have better seeing conditions. And here we can see sky A as opposed to sky B, the same galaxy. We can see that it appears very blurry. So we have all that incoming starlight that's getting refracted and essentially giving us a pretty blurry image. So here are some other images of some different skies. So remember, from your first observation, you had to assess the magnitude of your sky. So the lower the number, the more clear it is, just like with stellar magnitudes. So here we can see magnitude 9, no stars. We start to see some with a 7, and we can see even a bright star Altair is not visible in these magnitude skies. And as we progress to a lower magnitude, we can see that we see a lot more objects here. We can see some of the dark sky Messier objects. We can see some of the bright stars. So we want the lower magnitude sky in order to observe. And around here, a really good location for that would be Mount Pinos. They have star parties there every other weekend all summer long that are totally free. I highly recommend it. So one of the other things that can cause atmospheric instability has to do with the flow of air. So if we have two different sites on either side of this mountain range, we can see that we have stable air that flows up the mountain, and as it descends down the mountain, we get this turbulent flow, and that can also increase the blurriness of an image. So from site A, we can see, just looking at Jupiter, a really clear view. We can see all of the different banding, the atmospheric banding, which all correspond to different pressure zones, and then we see them as different colors. And we can see at site B, you really can't see the flow of gases that you can really see clearly in site A. So some of the best locations for a telescope are far away from civilization. So as we can see here, we have all of this blue. That blue are large cities. So that would not be a good spot to put telescopes. However, we have many in this blue. We have another famous one up here. And that's because those were built a long time ago, like Palomar, Mount Wilson, the Peck Observatory up in the Bay Area. I got to see that this summer. So California has been crucial to a lot of astronomical discoveries, and we have some pretty famous telescopes and some of the most widely used telescopes in the world, but they are now currently in urban areas. Palomar and Wilson are high enough elevation to where there's still some really good astronomy done from those. They're high, they're above a lot of the city lights, but Mount Wilson is right above Pasadena, which is very close to Los Angeles. But that is where one of the most crucial discoveries in all of astronomy, the expansion of the universe, that was done right here, where we now have lots of city lights. So this is actually a telescope. This is somewhere in Europe. This is a pretty old one. Imagine climbing those steps to get to it. So you want really dry air. So deserts are really good places. You can see this guy has a dome on top, so there would be one dome there. Here we have Mauna Kea. So this is a pretty high elevation. People actually get altitude sickness there because it is so high. There can actually be snow there because it's so high. All of these different observatories are actually owned by different countries. So the U.S. owns a couple. Japan has the Subaru telescope. Subaru actually means Pleiades, Seven Sisters, which is a constellation. So we have multiple different domes. It's a real international cooperation there. The other place would obviously be in space, when you're above all of the atmosphere and where different wavelengths of light can penetrate through. But that is a lot more expensive. So mountaintops where we can just put a standing dome, or in space, are really the answer to get better skies, better seeing, and also different wavelengths. Because high elevation, you can still see some UV and some infrared that you couldn't see at ground level. But then in space, we have all of the other astronomies, all of the other wavelengths that are blocked by our atmosphere. So this is in Chile. This one is also in a desert, very high elevation, very dry. This is also about 14,000 feet. That is it for today.